Section 7.1 is an introduction to theoretical and experimental probability. I would pause the video and write down all these vocab words. So probability is the likelihood that something will happen, how likely something has happened. The notation that we use is P of A, where A is whatever your event you're talking about. So this is saying the probability that event A occurs. Subjective probability is judging the likelihoods based on past experiences, like if you know something has happened before, and then judging the probability based on that prior knowledge. Experimental probability is judging the likelihood something will happen based on an experiment. So you can conduct an experiment, and then based on that experiment, you give your results and your probability of that. An experiment is a process for which you obtain an observation, whether that means flipping a coin 100 times or rolling 3 dice or whatever it is. Trials is how many times you repeat that experiment. So if you flip a coin 100 times, there would be 100 trials. Outcome is the result. So I flipped a coin and I got a heads. That's the outcome. Equally likely outcomes are outcomes that are all equally likely to occur. So for example, if you flip a fair coin, there's a 50-50 chance of a heads or a tail, or rolling a fair die. Event is the outcome or set of outcomes. So for example, if I want to find the probability of flipping a heads, then heads would be the event. Usually we denote it with some capital letter. And then sample space is the list of all possible outcomes of an experiment. And we denote the universal sample space, the everything, all possible outcomes, with the capital letter U. So here we're going to be talking about the difference between experimental probability and theoretical probability. Experimental probability, as we defined on the previous slide, is based on an experiment that you perform. It's also sometimes called the relative frequency. We saw this in chapter 8. So if you flip a coin 100 times and you want to know the frequency of the event, so for example, you ended up flipping 47 heads, then the probability would be the 47 heads divided by the 100 trials, and that would be your experimental probability. Theoretical probability is mathematical calculation on the probability based on the possibility of outcomes and the possible total number of outcomes. So the probability of event A, P of A, is equal to how many total outcomes fulfill event A divided by the total possible outcomes in the entire sample space. So again, if we're talking about flipping a heads, then N of A would be all the ways that you could get a heads versus divided by all the possible outcomes. So 1 heads over 2 possible outcomes, heads or tails. Probability is a number that's between 0 and 1 if you write it as a decimal, because it's a percentage. What's the percentage that something is going to happen? Expected value is the expected number of outcomes you would expect to happen. So again, flipping a coin, if you flip a fair coin 100 times, you would expect 50 of them to be heads and 50 of them to be tails. So that's your expected value. So here's an example. We want to find the probability of each event and decide which event is least likely. We're going to assume that all the dice are fair. When it says a 4-sided dice, you're going to go numbers 1 through whatever side it is. So a 4-sided dice would have numbers 1, 2, 3, and 4. So for event T, we want to find the probability that you throw a factor of 24 on a 4-sided dice. So first thing I'm going to do is I'm going to write out the possibilities, the events. So our sample space, all our possible outcomes for a 4-sided dice would be 1, 2, 3, and 4. So N of U, or how many possible outcomes there are in the sample space, would be 4. There's 4 total outcomes. For T, a factor of 24, well, all 4, 1, 2, 3, and 4, they're all factors of 24. So 1, 2, 3, and 4 is our event. Okay, what could possibly work for throwing a factor of 24? So N of T, the number of possible outcomes, is 4. So if I want to find the probability of T, it's N of T, how many ways that the event can happen, 4, out of N of U, the total number of events, which in this case is also 4. So the probability of throwing a factor of 24 on a 4-sided dice would be 1. So go ahead and pause the video and try the next 4. So for O, we're throwing a prime number on an 8-sided die. So an 8-sided die would mean that our sample space is the integers 1 through 8. And then prime numbers, the prime numbers between 1 and 8 are 2, 3, 5, and 7. 1 is not considered prime. So our sample space has 8 total possible outcomes, and our event, throwing a prime number, has 4 possible outcomes. So the probability of throwing a prime number on an 8-sided dice would be 4 out of 8, or 0.5. So if you haven't already done so, go ahead and do D, C, and I. So for D, our sample space is the integers 1 through 12. So the number of total outcomes in the sample space is 12. We want at least 11, so that would just be 11 and 12. So our number of outcomes in our event would be 2. So the probability that we throw at least an 11 on a 12-sided dice would be 2 out of 12, or 0.167. For C, we're throwing a 6-sided dice, so our integers 1 through 6 is our sample space, so our total number of outcomes is 6. We want to throw at most of 3, which means 1, 2, and 3, so the number of possible outcomes in our event is 3. So the probability of throwing at least or at most a 3 on a 6-sided dice would be 3 out of 6, or 50%, 0.5. And then the last one, throwing a multiple of 5 on a 20-sided die, so our sample space is integers 1 through 20, so 20 total possible outcomes, and throwing multiple of 5, that'd be 5, 10, 15, 20, so there's 4 outcomes in our event. So the probability of throwing a multiple of 5 on a 20-sided dice is 4 out of 20, or 0.2. So then the one that's least likely to occur is just the one that's the smallest, and so that would be D. 16.7% is the smallest probability, so that is going to be our least likely to occur. You could leave these in fraction form, or you can plug them in the calculator and get the percentage in decimal form. So now we're going to do some examples based on expected value. So we're flipping a fair coin 14 times, and we want to predict the number of times you would expect a head to be face up. So go ahead and pause the video, and if you flip a coin 14 times, how many times would you expect a head to show up? So if you're flipping a fair coin, there's only 2 choices, heads or tails, so there's a 50-50 chance for it to be heads up, and if you flip it 14 times, you would expect heads to be face up 7 times. So the expected value is the number of trials that you're doing times the probability of that specific outcome or that event. So in this case, it would be 14 times a half, so that's where you get 7. For number 2, it says the statistical data built up over 5 years shows that the probability of a student being absent from school is 0.05. There are 531 students at the school. For part A, we want to predict the number of students we would expect to be absent on any given day and interpret that. And then part B says state the assumptions for supporting your answer. So go ahead and pause the video and do number 2. So for the expected value, in this case, number of trials is how many students there are. So there's 531 trials or students, and the probability of any one student being absent is 0.05. So if you multiply those two together, you get 26.55. You could leave it that way because it's an expected value, but if you round that to the nearest whole number, because you can't have 0.55 of a student, you'd expect 27 students to be absent on any given day. So that's the expected value. Any assumptions, there's a few assumptions that are being made. One is that every student has an equal likelihood of being absent, which isn't really true. There's usually students who are, present every single day, and there's students who have some more absence problems. And then also that every single day has an equal likelihood of absences, which again isn't really true. Days around breaks are more likely to be absent than a regular normal school day. So here we have a data table that shows data for a coastal town that carried out a survey of tourists in July of 2018. The accommodation type chosen and the age of the tourists were recorded, and it was given in this table. So we have 4 different age groups, 18 to 30, 31 to 50, 51 to 70, and greater than 70, and 4 different accommodation types, hotels, camper vans, tents, and apartments. So for part A, a tourist is chosen at random from the survey to receive a promotional offer. Determine what age group the tourist is most likely to belong to and why. So go ahead and pause the video and figure that one out. So for part A, if the tourist is chosen at random, which group are they most likely to belong to? Well, I added up the ages here, or the groups for each age group. So the frequency that was the highest was the 31 to 50. So that's going to be the most frequent age group, so that's going to be the one that's most likely. So for part B, we want to find the probability that the tourist chosen belongs to this age group and express your answer as a decimal. So go ahead and pause the video and find the probability that the tourist belongs to the 31 to 50-year-old age group. So for probability, I totaled up how many total responses there were. So I added up all these age group frequencies that I had, and I had a total of 1,330 responses. So then for the probability of 31 to 50, there were 529 31 to 50-year-olds out of 1,330 total respondents. So then the probability that someone fell in the 31 to 50 age group was 0.398, or 39.8%. So the last part, Part C, says that in July 2019, 16,000 tourists are predicted to visit the town. If the town's hotel has a capacity for 5,000, predict whether or not the town has enough hotel capacity to meet the demand. So you're finding expected value based on hotels. So go ahead and pause the video and try that. So for Part C, we want to find the expected value given that they're going to have 16,000 tourists. So the first thing I did is I figured out what the probability of a tourist picking a hotel is. So there's 370 total tourists that picked hotels out of the 1,330. So I have the probability that someone picked a hotel is 0.27819, 370 out of 1,330. So then the number of trials is how many tourists there are, 16,000, times the probability that they'll pick a hotel, ends up being about 4,451 hotels. So if there's 5,000 hotel rooms, then we should be good. So experimental and theoretical probability, just an introduction. The probability that something occurs is the probability or the amount of outcomes that affect your event or that are your event divided by the total number of outcomes possible.